Hey, folks, it's Mash, and today we're going to be doing 2023 Higher Chemistry Paper 2. So I've already done Paper 1 before. I might leave it in a link in the description. I usually forget to do so, though, so sorry about that. But yeah, so this is the full Monty. This is the 95 mark paper, and you have to write in sentences. But it's not awful. It could be a lot worse. So remember, folks, just stick in, try your best, and put something down for each question, even if it's completely insane. It's a good strategy. But we can use a calculator, and yeah, we'll get straight into it. So, elements are arranged in the periodic table in order of increasing atomic number. Many physical and chemical properties of the elements show periodic trends. So what it means by periodic trends is if you move around the periodic table, stuff changes. So, for example, I've got my data pocket over here. We'll go open up the periodic table. You know, if you move to the right, number of protons increases, move down, number of occupied electron shells increases, and then yeah, everything's divided into groups. So that's what it's on about periodic trends. First ionization energy is a property that has a periodic trend. The diagram shows part of a graph of first ionization energy against atomic number for some elements in the periodic table. Explain why there is an increase in first ionization energy from the elements D to K in the diagram. So we can see D to K here. As you increase the atomic number, first ionization energy goes up. So what does this mean? Well, why is this? It's because adding protons to number of protons increases as atomic number increases, because they're basically the same thing, but I'm really dumbing it down here. Increases, meaning stronger nuclear charge. So this is like the charge on the nucleus. Charge. Exerting. I love the word exerting. More force on the electrons. So more energy is required to remove them. There we go. So I've probably overcomplicated that actually there. But as you know, it's always better to write more than write not enough, right? So, because it just says here on the marking scheme, you can just say increasing nuclear charge, and that would actually get you. So I've got like 3 marks there. But just to really help you guys understand it, I've padded all the table. Anyway, I'll stop blabbering on. We'll move on to number 2. State an element from A to M in the diagram that represents an element from group 7. Okay, so group 7 is going to be at the end of the periodic table here, almost at the end, the halogens, and it would just be before group 0, I guess, where they would not, which is like the noble gases. So the way we can tell this actually is, well, if I go down here, we actually look at the actual first ionization energies. We can see that it just increases completely across a whole period. Like so, group 7 would be group A 0, the noble gases would be the highest ones. With full complete outer shells, so they'd be like C or K. So group 7 will be the ones before them, so it'd be B or J. So you can write any one of them. I'm just going to say B because it's cooler, I think. Sorry, I'm a bit of a J hater, but yeah, it's B or J. You can do whatever you want. Oh yeah, I'll include J as well. There we go. So anyone is fine, but it's an element, so probably just best to put one letter. Don't go B or J. The table shows 4 ionization energies of sodium. Explain fully the large increase between the first and second ionization energies of sodium. So yeah, and you can actually see they've just been taking numbers from this table here. But and like, why is it times by 4? Well, the way we answer that is if we have a look at sodium's position in the periodic table, this one here on page 8, we can see it's got 281, which means first ionization energy is so low because you're just taking it away from its outermost shell. But then, if you try to do the second one, you're actually taking it away from an inner shell, which is closer to the nucleus, and it's less shielded from inner shells. So it's very hard to remove. So that's exactly what I'm going to put. a second ionization. Oops. Energy for sodium involves removing an electron from an inner shell that is closer to the nucleus and is also less shielded from the force exerted by the nucleus. Oh man, I'm so good at this. There we go. Exerted by the nucleus by inner shells. Boom. Alright, that's what you need to do when you get your 2 marks. Use the information in the following table to determine the enthalpy change in kilojoules per mole for the following reaction. And we can see, we go through here, we have ionized sodium going to even more ionized sodium. So what this means here is that we've already done the first step. So we don't need to include that. That's already been done because sodium's already ionized. And then we're going to be going to the second and third ones, but not the fourth. And remember, so we need to add these 2 numbers together because they're not summated, I think it's the word. You know, going if I put 6,910 kilojoules in per mole, that's not going to extract 3 electrons. It's only going to extract the third one. So we have to add these 2 together. And how are we going to do it? Well, we're not going to add it in our heads. That's for losers, nerds. We're going to use our calculators. And there we go. And it'll be 11,472 kilojoules per mole. So it'll be kg. And I've just realised the chemistry people are like actually nuts. You have to really make this J a lot bigger than the K. And then mole minus 1, so it's kilojoules per mole. And yeah, I've done it in a really poor way, but you get what I'm on about. Electronegativity is another property that has a periodic trend. States what is meant by the term electronegativity. I always have this kind of boilerplate standard answer, which is the tendency of an atom to attract a bonding pair of electrons. That's it. There's lots of ways you can state this, but it's basically along those lines. Explain fully why electronegativity decreases going down a group. So going down a group, if I go and put this, that would be just going down the way down this, right? So why does it do that? Well, because we've got extra shells coming in, which are shielding the outer electrons from the force of the nucleus, which means the nucleus isn't attracting like free floating bonding electrons as easily because they're further and further away. So it goes down. So that's exactly what we're going to say. We're going to say going down a group increases the number of occupied electron shells. Sorry. Which means that bonding electrons are better shielded from the force of the nucleus. That's good enough. I cannot spell to save my life. By inner shells. So electronegativity decreases. Oh, I need to. Sorry, I need to really I'm just like I use the marking scheme to really make sure I keep track of stuff. But what they really want to say is thus the attraction of the nucleus to bonding electrons is reduced. So no, it's a negative nucleus. Oh, bit of a long answer. Sorry. Suggest which of the group 2 elements is the best reducing agent. So remember, a reducing agent, right, is something that wants to help others get reduced, and reduce means lose electrons. So in fact, a reducing agent means that it should be something that oxidizes quite easily. Okay, so oxidizes means it wants to lose electrons. Figure that out, right? If you want to lose electrons, atoms want to get to complete their shells. That's why noble gases are so stable, because they've got complete electron shells. But if you want to get to them, what you can do is become an ion and either lose or gain electrons to get a full shell. So if you want to lose electrons to help others reduce, you want to be on this kind of side of the periodic table, group 1 and 2, or not. But it states here which the group 2 element is the best reducing agent. So that means that we'd want to have the lowest electronegativity possible, because we really want to get rid of these electrons. So that means we can pull up over here, we want the lowest electricity possible, and we know that electricity decreases going down a group. So group 2, first one I believe is beryllium. Beryllium's 1.6, but if we go down, we go to magnesium, and then we go down to all calcium, that's 1.1, then we have strontium and barium. So that means we can actually go all the way down. If we go back to our periodic table, we say, okay, well, we want to go down as far as possible, so the lowest one would be radium. And so we could say radium. Beautiful. Number 2. Question 2, I should say. Hydrides are compounds containing hydrogen and one other element. The graph shows the boiling points of group 4 and group 5 hydrides. Explain fully why the boiling points of the group 4 hydrides increase going down the group. In your answer, you should refer to your intermolecular forces involved. So, boiling points. So, if boiling points are increasing, that means intermolecular forces must be increasing, because it means more things are. Yeah, there's more stuff to break, right? So we could look at this. The only difference between them is the elements, but they're all from group 4. So we need to figure out why these are increasing. Well, if we look on this again, right, we've got it's carbon, then silicon, then germanium. Carbon's got 6 electrons. Silicon has 14. Germanium has quite a few. That's 32, I think. And then so on and so forth. So each of these are getting progressively more electrons. So that means if there's more electrons, then LDFs are stronger, which means that there's more energy required to break the forces between the molecules, which means boiling point increases. So let's go and write that down. Going down group 2, group 4, elements increase the number of electrons in their atoms, meaning that LDF, I'll put brackets in the dispersion forces because it's probably best to do that rather than just saying the acronym. Stronger because the temporary dipole is more extreme, because the reason they're stronger is because that means that when the electrons do shift onto the other side randomly, they'll have a higher there'll be more charge because there's more electrons, which means higher electrostatic forces. But I'll just kind of simplify to just be temporary dipoles are more extreme. Have a more extreme charge differences probably. Thus, the forces between the molecules are stronger, so require more energy to break. Thus, boiling point increase. And there we go. I was just double checking I'm not going insane. But name the type of intermolecular force that is responsible for the anomalous boiling point of ammonia, NH3. So yeah, you look at this, ammonia is way higher than it should be because all these are kind of straight lines. So if we were to like kind of, ammonia should be like down here and then it's like increase, but it's way higher than it should be. And that's because instead of following the rest of the rules, it actually uses hydrogen bonding. Because it's hydrogen is bonded to nitrogen, oxygen, and fluorine, which means you get hydrogen bonding, which is far stronger than the PD, the permanent dipole interactions you get with the other hydrides. So that means that yeah, a bit stronger. But we just need to say hydrogen bonding for this question. Silicon hydride, Si4H. H4, sorry, I don't know what happened there, can be formed by reacting silicon with hydrogen. Calculate the enthalpy change in kilojoules per mole for this reaction using the following information. Oh, goody, I actually quite like these questions. Maybe I'm just going insane having a favourite chemistry question, but there's just something about them. So what we want to do is we want to use these equations to get this first question by flipping around and cancelling stuff out. So I'm going to go question by question and see if we need to do anything weird here. But I'm noticing for this question here, we've got silicon hydride on the left side, but we want to be on the right. So I'm going to write this symbol here. This means we're going to flip this whole equation around, and this will become important later. Now Si, that's on the correct side, and is that's the same multiple. So this one I think is just completely fine. And the second, this third question equation here, we do have hydrogen, which is on the correct side, but it needs to be 2H2. For this equation, so I'm going to times it by 2. Okay, so I'm going to read out this top equation in the other way around, just so we can get it. I'm not going to put state symbols because that's for losers, and there's no weird state changes in this one because some of them you do get weird state changes where state symbols are important, but I don't see any here, so I'll just continue as is because I don't want to have to write any more than I have to. So, and then I'll add 2 here, and this is 1, and this is 2. So, now that we've flipped this over, we can start cancelling stuff out. But first thing I'm going to do is make sure that we have all those ingredients. So, yep, we do have Si. It's on the correct side. We do have 2H2 on the correct side, and we do have SiH4 on the correct side. Now, I need to see if we can cancel every other ingredient. So, we'll also the equation if we've written it down here. So silicon oxide, yep, we've got those two can cancel each other out because they're on opposite sides, as you can see. We've got O2 over here, but what are the different numbers? But remember, that's 1 there, so it's actually 2 O2 altogether. So I'm going to put a big line through it and all. And now we just need to get rid of these 2 H2s, which we've all are on different sides, so we can cancel them out. So that means we've got an equation that actually works. And all those just preambles to just so we can figure out what to do with these. So now we need to add all these together, but we need to, because we've flipped certain times around, we need to mess around. Now, if you flip an equation, the enthalpy change will just be the same, but the sign will be flipped. So instead of negative 1,517, it will be positive 1,517. Now this equation we didn't change anything, so it'd still be 9 minus 911. And then the next one we times by 2, so it'd actually be 2 times negative 208 d6. Boom, and now we just need to go and compute this. And we'll get 34. And we're going to put kilojoules per mole. There we are. And yeah, I've heard rumors that they'll end your life if you don't make the J taller than the K. So I'll just quickly do that. But there we are. One method of propelling in silicon hydride involves reacting magnesium silicide with hydrochloric acid. 15.32 grams of magnesium silicide was reacted with excise hydrochloric acid. 2.56 grams of silicon hydride was produced. Calculate percentage yield of silicon hydride. So, when we talk about percentage yield, what we're essentially saying is how much did we get in comparison out of how much we could have gotten out theoretically. So, we do get 2.56 produced, but we want to figure out what we could get theoretically. So if all the magnesium silicide reacted perfectly and we extracted all the silicon hydride beautifully, how much would we get? So let's go and figure that out. So we're going to go and calculate the number of moles of magnesium silicide we put in. So we had 15.32 divided by 76.7, and we'll quickly do that. Beautiful, it's 0.119 something or other. Just keep this in your calculator, don't bother right now. I'm just going to put dots actually after, because they'll only reward you for the final answer. But we've got that, and we'll just leave it in our calculator, because then there's less chance of making mistakes as well. So then it's a 1-to-1 molar ratio. 1 mole of this will create 1 mole of that. So that means we can just do the same equation again without making any. This is what we already do, is replace the general formula mass with silicon hydride 1. So 0.1997 ... equals some mass over 32.1. So mass would equal 32.1 times what we got, and that would be 6.4 something. 1, 2, we'll say. Fantastic, and it's in grams, remember. But we're not done yet. So we figured out the paragraphs, but we actually need to calculate the percentage yield. So how we're going to do that? Well, we're going to go over here. I'm going to say percentage yield is percentage. We'll just say Y percentage. And then we're going to have actual yield. I'm just going to say actual because I'm running out of room. And then theoretical yield, theo, and then it's times by 100. Cool. And then we're going to put what, so actual yield was 2.56 over, we think we could have gone on 6.4, 6.412, and then times by 100. So what do we get? I'll go and copy this for use later. Times by 100, we're going to get 39.9, so that's what I'm going to write, 0.9%, and there we are. The table shows the melting point of silicon hydride and silicon oxide. Explain fully why silicon oxide has a much higher melting point than silicon hydride. I wonder why this is. Well, silicon oxide should immediately light something up in your brain because it is a covalent network molecule. And that means that all the molecules, all the atoms in there are held together by covalent bonds. There's no intermolecular force. The whole thing is just one big blob. And this means that it has ludicrously high melting points because you have to break the very strong covalent bonds rather than just breaking weak intermolecular forces. So yeah, that's exactly what we're going to write. So silicon oxide is a covalent network substance. There we go. So to melt it, covalent bonds. Jesus Christ, I can't do this. Bonds need to be broken, which requires lots of energy compared to the weak intermolecular forces that hold silicon hydride molecules together. This means that the melting point of silicon oxide is much higher than silicon hydride. I'll just fix my grammar. Compared. Compared to breaking. So I'm just making sure this makes perfect sense. Breaking a weaker nitrogen forces that holds the silicon hydride molecules together. And that should do it. Right, move on to 3. Cheese, my favourite subject, is a complex substance containing a wide variety of chemicals. The structure of a fat found in cheese is shown below. The alcohol needed to form fat molecules is glycerol. State the systematic name for glycerol, and this is something you could just copy and paste every time. Stay with me now. Propan 1, 2, 3 triol. I think it might be propan, but no, there we go. It's right there. And it does accept propan 1, 2, 3 triol. I think I do want you to say propane 1, 2, 3 triol, but whatever. It's this. Name the type of reactions used to form fat molecules from fatty acids in glycerol. And that would be another thing you're just going to remember is condensation, because fatty acids are basically carboxylic acids, and glycerol is basically a fatty alcohol. So basically, you're going to, when you make fat molecules, you're making an ester out of when you combine a carboxylic acid and an alcohol in a condensation reaction. And you can also say esterification if you want to be cool, I guess, but come on, condensation is the way to go. Fatty acid W reacts as shown. Okay, and identify the functional group circled in molecule X. And this should be pretty obvious. It's going to be a carbonyl group. And when you ever see a double bonded oxygen to a carbon, it is a carbonyl functional group. Name molecule Y. So we just got to state the systematic name for this molecule here. So whenever you're doing carbon compounds, first step is to count how many carbons there are. 1, 2, 3, 4, 5, 6, 7. So our base is going to be hept. I always heptan. So that's our base that tells us how many carbon atoms there are. And I don't see any double bonds. They're not edited apart from obviously the double bonded oxygen. And since it's not on a terminal carbon, it's in the middle, it will be a ketone. And it's on the second carbon atom, which means it'll be heptan 2,1. Identify the type of reaction used to convert molecule Y into molecule Z. So you can see molecule Y, it is heptan 2,1, and we're converting it into an alcohol, so it'll be heptan 2,0. So remember, I said this in the previous videos, it's basically if we're oxidizing stuff, we get a alcohol. I'll represent it as a OH group, I'm sorry. If we want to oxidize it, we get to a ketone aldehyde, which I'll represent as a carbonyl group, and then if we go oxidize further, we can get into a carboxylic acid, which I'll represent as a carboxylic acid group, carboxyl group. So this is oxidizing, but as you can clearly see here, we're going backwards. We're going from a carbonyl group to a hydroxyl group, which means it must be the opposite of oxidation, which is, say it with me now, reduction. Boom. State which of the reactions, 1, 2, or 3, results in an increase to the oxygen to hydrogen ratio. Okay, so now look at this one. So which one would actually increase the number of oxygens per number of hydrogens? Well, look for here. If we 2, right, we're just reducing the amount of oxygens. We're getting rid of this whole group here, so that's no good. And then down here we're adding another hydrogen, which would reduce the amount of oxygens per hydrogen. So those two aren't good. So if we look at 1 though, we're adding an oxygen on to something else, which would increase the oxygen-hydrogen ratio. There's more oxygens per hydrogen, which, yeah, it's exactly what we want. So we're just going to say reaction 1. Fatty acids can be converted into hydroxyl carboxylic acids. An example of a hydroxyl carboxylic acid is shown. The two functional groups in a hydroxyl carboxylic acid react together to form a cyclic ester. An example of a cyclic ester is as shown. Draw the structural formula for the hydroxyl carboxylic acid that can be used to produce a cyclic ester. Oh boy, I hate that term so much. It makes me want to do something horrific. So basically what I have to do is kind of unwrap this and turn it back into its original form. And we're looking to get something that sort of vaguely resembles this. So a molecule with both a hydroxyl group and a carboxyl group. So I'm going to go and just start writing out. So at this end, I'm going to have my carboxyl group. And then we go 2H, 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 and then it looks like we'll have our alkyl group here. Okay. Alkyl group, hydroxyl group. So that we C, and then OH. And then probably best to actually put it to the side maybe. And then C, so 3 more C's. And then all we have to do is go and populate these C's with hydrogen. And then commit the almighty sin of writing in the markers column, which you shouldn't do in an exam, I must say, but I'm doing it here because I can. No one's marking my paper. So there you go, and that's the full thing. Scrolling down. The flavour of cheese changes over time as the concentration of the flavour molecules change. Gas chromatography can be used to analyse the concentrations of flavour molecules. Chromatograms for 2 samples of cheese are shown below. Define the retention time in minutes of the peak in the chromosome X that is missing in chromosome Y. And this should be nice and simple. So I got hair in my mouth I'm trying to get rid of. But yeah, what we have to do is like identify the peak. Okay, well, I found it. So when is it? Well, it's kind of just a bit past the first mark. So this should be a bit past 12. So we can probably say 13 in between. Yeah, but say 13 because it's kind of in the middle. So let's go and just put 13 minutes. Right, and we'll move on to the next question. The following chromogram was obtained from another sample of cheese. The concentration of a flavour molecule in cheese can be determined by calculating the area under the peak that corresponds to that molecule. The concentration of flavour molecule 3 cannot be determined from the chromogram, suggests what would be needed done from the sample to allow the concentration of flavour molecule 3 to be determined. Right, well, if you look at this thing, the concentration of the flavor molecule free is ludicrous. Someone's really added a lot of this stuff, right? So if it's going off the scale, it's that bad. It's not actually complete. It's cut off. So the only way we're going to be able to measure the concentration is if we dilute the sample, which would bring all these peaks down so we can actually see what free is. Right. The main protein of cheese is called casein. The diagram shows part of the structure of a casein molecule. The table shows the relative proportions of the amino acids found in this section of the protein. So we've yada yada, okay. Leucine and valine are amino acids that must be obtained through the diet. The stated term for this type of amino acid, this is another thing you just can't remember. It's essential amino acids. So yeah, essential amino acids, stuff you need to get from the diet. Don't confuse them with essential oils. But yeah. Using information from the diagram and the table, draw a structural formula for glutamic acid. Okay, so glutamic acid is, we need to find it on this. And we know its relative proportion is 2, so we should find 2 of them in this thing. So we just have to go through, and okay, well, that one here repeats. That one repeats, and then those 2 repeat as well. All these other ones are non-repeating. So it has to be one of these 2. But it's glutamic acid, which means it's going to be an acid. So we can actually discard those 2 and figure out, okay, well, it's this. Now what we all need to do is unbind it from its amide link and see what we get. So, well, we're going to have to put another hydrogen on this nitrogen and then put a OH group on this carbon. So we have nitrogen over here, and 2 carbons. This would be, this is going to look like an acid. H at top, and then we can write down whatever it was, C2, CH2, CH2, and then, okay, so it's going to be no, I've flipped this up. That's not how anything works. And then we have it. So might want to fix this down here. It's a bit of a disaster size, but yeah, that's the general idea. When the cheese is heated, the protein changes shape. This take the term used to describe this process. And there's another thing you just got to remember: denature. So this is when the basically what denaturing is that you have intermolecular force between the amino acids. They kind of get attracted to each other, and this folds the big chain in various ways. But if you denature it, you can break those forces and kind of straighten the whole thing out, which is called denaturing. Processed cheese is made from cheese, soluble milk proteins, and water, and an emulsifier. State the function of an emulsifier. So basically, this an emulsifier allows an emulsion to stabilize and not separate into layers. But what we can do to really improve our answer is say, just put in brackets, non-polar and polar liquids, dispersed through each other. From separating these layers, just so it really matches with what the marking scheme says. A compound added to cheese is a mold inhibitor and has the formula C plus 2, CH3, CH2, COO. So this looks like to me a soap. But what is it? Well, Ca, that's going to be calcium. So we can probably actually just write that. If I knew how to spell calcium, that is. There we go. So what about the other one? Well, we've got 3 carbons, So it's probably going to be propan something, and then it's going to be O8. So think of it like it's sort of like an ester, right? So you have ethyl propanate, and it'll be calcium propanate in this one, compared to because this is a salt, not an acid, so it wouldn't be propanoic acid or something. It would be propanate. All right, we'll move on to 4. Oh no, it's a 3-mark open-ended question. Whatever are you going to do? Volumetric analysis involves using a standard solution in a reaction with a well-defined endpoint to determine the concentration of another substance. Correct use of the appropriate apparatus and solutions is essential to ensure accurate determination of the concentration by titration. Using a knowledge of chemistry, describe the experimental procedures, including equipment used to accurately determine the concentration of the substance by volumetric analysis. Ooh, okay, right, so... as with all of the open-ended questions, they're open-ended, so you can write basically anything you want, so as long as it, answers the question. But you really want to make sure to show off your good chemistry by writing as much cool stuff as possible. Okay, so we just basically need to go and describe a titration. So the substance, which concentration is desired to be determined, is called the analyte. And the standard solution of known concentration is called the titrate. A sample of the analyte is put below a burette, which is filled to the 0 cubic centimeter graduation mark with the titrate. To begin, a rough titer is done. So rough titer done where to gauge the rough level of titrate needed to react completely with the analyte. How you spell that? I've already forgotten. Yeah, that'll do. This titer is ignored in the average. Alright, and then you do the proper titers. Done far more accurately. Usually going drop by drop until the reaction is completed. Doing this multiple times, then averaging the results. Means that the concentration of the analyte can be determined by calculation. Fix that. As the equation for the reaction can be used to determine the molar ratio between the titrate and the analyte, and then the volume and concentration of the titrate can be used to calculate the number of moles of the titrate, which is then used to calculate the number of moles of the analyte, which then the volume tested can be measured. Oh, that's enough. I need to talk about the graduation flat of the volumetric flash, don't I? And I'm slowly losing. Use the number of moles of the analyte, which can then be measured to calculate its concentration. So best thing to do here is whenever you're doing, basically in chemistry and especially for physics, if you're doing these things, make sure you put our equation in. So I'm going to be using N equals CV because that's what we've been using, and then we're going to define the terms. N equals number of moles, C equals concentration. The army we're going to put in the units, which is moles per liter. And then volume liters. I think we've almost done. I think I'll just talk about volumetric flasks. The analyte. Yeah, I'll say a sample of the analyte is taken and put in a volumetric flask. Is then filled up to the, a volumetric flask, and filled up to the graduation line. Yeah, that's probably enough. It's a bit disjointed, I'll be honest. It's not one of my best answers, but this should give you quite a few marks. Just keep rambling on about volumetric analysis and you'll get there. Oh, and it's deleted. That's actually really, that's not a bot, guys, I swear. It's a, there we go. Like magic, it's back. Oh, I had a heart attack there. Right, we'll move on to 5. Oh, it's just, no, it hasn't. Number 5, gin, everyone's favourite substance, is made by flavouring a mixture of ethanol and water with plant extracts. The mixture of ethanol and water is made by fermentation followed by distillation. In fermentation, enzymes and yeast convert glucose into ethanol and carbon dioxide. The equation for fermentation is shown. So, a 50 cubic centimetre sample of glucose solution contained 5.79 grams of glucose. Calculate the volume in litres of carbon dioxide gas that will need to be produced if 16 litres of this glucose solution were fermented. So I'm going to have to write quite small because there's a few calculations we're going to have to do. So first thing I'm going to do is calculate the number of moles of the glucose. That'll be 5.79 over 180. Let me just put my calculator, put that in. .0.032, yeah, yada yada. We'll just leave it on our calculator for the time being. And then what we're going to do is calculate the concentration of glucose. Because we know what moles there are. Concentration we don't know, but we do know the volume, and it's going to be, we have to put it in litres though, so it's going to be 0.05, not 50. And then C would equal something. So let's go and divide by 0.05, and that will give us this number. So concentration is 0.64 free mole per litre. So once we do that, we can figure out the number of moles in 16 liters. So I'm going to say N equals CV. Concentration is 0.643 times our volume, which is 16. Let's go and do that. So then we have 10.3 moles. Now we have 10.3 moles of glucose, and then we're going to convert it into carbon dioxide. So carbon dioxide is a molar ratio of 1 to 2, so we're going to times by 2. So we end up with 20.6 mole of carbon dioxide, and then we can use the molar volume, which is N equals P over molar volume. So our moles, it's going to be 20.6 over volume, while our volume is going to be 24. So volume is something, and that something is this number here, 494.1 litres. So yeah, quite a large amount of carbon dioxide. Calculate the atom economy for the production of ethanol. Okay, so the atom economy, remember, I'm going to represent it as percentage AC, is equal to the mass of desired products over the mass of reactants. Fantastic. Right, let's go and run this through then. So it's production of ethanol, so our mass of desired products, we want to get this, and then our reactants will be this. So yeah, let's go and start adding them all together. So this is our reactants would be 180, because that is our, yeah, we're just fermenting glucose, and then we have 2 times 46 of what we want, and the rest is going to be carbon dioxide, and that's 49, and then times by 100. So I've made this fraction far bigger than it has to be. So 2 times 46 is 92, divided by 180, and then we've got to times by 100. We get a 51.1%. Moving on to 5A2. The percentage of alcohol by volume can be calculated by measuring the specific gravity of samples taken before and after fermentation. Specific gravity is measured using a hydrometer. Level of sample on the hydrometer scale, read at eye level, is specific gravity. Percentage of alcohol by volume can be calculated using this formula, which has percentage of alcohol by volume for this sample. So all we need to do is plug our numbers in here. So we need to figure out the change in specific gravity, and that's basically just reading the graphs. Remember, it's the bottom of the meniscus, but in this case it doesn't really matter too much. So before fermentation, we're sitting at looks like 1.0.75. So it'll be something along the lines of this, and then this one down here looks like it would be 0.99. Oh no, it's be 98. Be 985. So it'll be the difference between these two. So let's just go and write that in. Oh, fiddlesticks. I'm really good at drawing fives, I swear. And then divide the whole thing by 0.7362 times 100. Right, and then we can go and just do this. So let's just go and calculate the difference. We get 0.09 divide by 0.7362. Get this number, and we're going to times by 100. And we're going to get 12.2%. Which is alcohol per volume, but doesn't need anything else. Plant material is used to flavour the ethanol and water mixture. The mixture is then distilled. The first fraction from the distillation contains toxic methanol and propan-2-on and is discarded. Describe a chemical test with the expected result for both compounds that can be used to distinguish between methanol and propan-2-o. Okay, so we're going to have to go and figure out chemical tests, and the basic idea is to distinguish between them is that you can oxidize methanol, but you cannot oxidize propan-2-on. So maybe what we can do is use hot copper oxide. So copper oxide, use what? Copper oxide. If the substance is methanol, a color change from black to brown, because it would be taking away the oxygen atoms from copper. It would be brown to, like, you know, the kind of the brassy color of copper would be visible. But if the substance was propan-2-on, then no color change would be visible. And there we are. You could also use acidified dichromate, but no one likes acidified dichromate at all. So we'll be using good old hot copper oxide. The second fraction from the distillation is collected for bottling as gin. Some of the plant compounds that give gin its flavour are shown. Name the class of compounds to which unsaturated hydrocarbons such as limonene and myrcene belong. And that would be terpenes, everyone's favourite. Well, not really mine, but you know, they're right. But you can just clearly see how this really like leaps out of you. But out of me. But main way you distinguish terpenes is that they're, if you count up all the carbons, there'll be a multiple of 5. So, for example, limonene, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Myrcene, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so forth. Circle an isoprene unit on the limonene structure below. So we need to go and find a section of 5 carbons. Yes, but remember, it's 4 in a linear chain and then 1 in a branch chain. So we can probably go and do this one right here. We can also circle this other one here for instance, but we're just going to circle 1. C. General acetate can undergo hydrolysis to produce an alcohol and another product. Name the other product. Okay, well, this general acetate can produces an alcohol, so general would probably be the product, so it would be acetate would be whatever this other one is. So maybe it would be acetic acid. We're just going to remove the 8 and add acetic acid. Now what you could also done is just looked at this diagram here and figure out, oh, it would be ethanoic acid because you'd split it there and have a OH. And surprise, surprise, acetic acid is the same name for ethanoic acid, which is itself the chemical name for the colloquial vinegar. So there you go, there's a fun fact for you. Gin is often mixed with tonic water before drinking. Tonic water contains quinine, a bitter tasting compound. Historically, quinine was used to treat malaria. To treat malaria, an intake of 10 milligrams per quinine per kilogram of body weight is required every 8 hours. State the mass of quinine required by a 70 kilogram adult in 1 day. This is just going to be a wee bit of maths. It should be pretty simple. You know. So 10 kilograms per kilogram of body weight required every 8 hours. So I'm going to say, well, 10 times 70. So this is required every 8 hours. We're going to need 700. But then 24 hours is made up of 3 8 hours, because 3 times 8 is 24. So that means we're going to have to write 700 times 24, which is not what I meant. I mean 3, sorry. So let's just go and do that. With 2100 milligrams. There we go. So you could have said, oh, just 2.1 grams. That's not that bad for 2 marks. 6. Ammonium nitrate is a commonly used fertilizer. Ammonium nitrate is made industrially by adding nitric acid, HNO3, to ammonia, NH3. Complete the diagram to show the shape of the enthalpy diagram for this reaction. Okay, well, it says here that the enthalpy change is negative, which means it's an exothermic reaction, and it means that we'll have less potential energy in the chemical than we had in the reactant, which means this thing is going to go down and then sit the products here. State the term for the unstable arrangement of atoms formed at the point labelled X on the potential energy diagram above. And this is something you just got to remember, the activated complex. I actually did not get this in my prelim, and I'm still salty about it. Oh well, what matters is the real exam, eh? 1,316 litres of nitric acid concentration, 9.5 moles per litre, were reacted with 220 kilograms of ammonia to produce ammonium nitrate. Show by calculation which reactant was in excess. Okay, so we've only got 2, and we've got 316 of this stuff, and then 200 grams of this. So we're going to have to use 2 equations. So we're going to have N equals CV. That's 9.5 moles per litre times 1,316. So let's just go and quickly do that. That's 12,502 moles. And their mole ratio 1 to 1, so we want to see which of these numbers is higher, effectively. Then we're going to use the mass, the mole mass equation. The mass is 220 kilograms, but we want to use grams, so it'll be 220,000. And then the uniform mass is 17. So that's what we want to put in. And that'll give us this horrific number. We can already clearly see it's going to be slightly higher than the other. So therefore, ammonia is in excess. Ammonium nitrate can also be produced by this reaction, by the reaction this nonsense. Suggests the reason why the method shown in part A2 is the preferred industrial route. Okay, well, if you have a look at this one, right, it's very simple. It's only 2 reactants and 1 product. So why don't we use this reaction? Well, because this gives 100% atom economy. Well, it's as much as stuff you put in, you don't get any weird byproducts you don't want. You get the thing that you want, no matter what. So that's what we're going to say. We're going to say it has 100% atom economy. The rate of reaction can be altered by changing the temperature or using a catalyst. Graph 1 shows the distribution of kinetic energies of molecules in a gas mixture. Suggest what is represented by the area under the curve in graph 1. That would just be the total number of particles. In the system. I get a second curve to graph on to show the distribution of kinetic energies at a higher temperature. Okay, so what we're going to have to do here is remember the total number of particles in the system stays the same, so the area underneath the graph stays the same, so you can't go crazy. But we also want to shift it to the right because more of them have an average kinetic energy. So it looks something like this, right? So it's still roughly the same area, but it'll have a lower peak at this point. So same area, but it'll be moved slightly to the right. In graph 2, the activation energy for the reaction, EA, is marked on the x-axis. Draw a line on graph 2 to show how a catalyst affects the activation energy. Okay, and this is going to be a nice and simple one. I'll put my line tool. A catalyst will provide a lower activation energy alternative reaction pathway. So it's like we're removing this line down here and put it there. I'm going to label it even. BC. Ammonia is used to produce ammonium nitrate that can be made by the Haber process. Reversible reactions, such as the Haber process, can reach a state of dynamic equilibrium in a closed system, stated by the term dynamic equilibrium, and this is again one of those definitions that you're just going to have to learn the old-fashioned way. It's just going to be the rate of Thorne reaction is equal to the rate of the reverse reaction. So that means that in effect nothing is happening to the concentrations because the reactions are both working simultaneously and doing the same effect. The ammonia produced is continuously removed. Explain how this will affect the production of ammonia. So that means that it will favour the forward reaction because there's no reactions go back. There's no ammonia, so the system will shift to produce more ammonia to fill the gap, which would increase efficiency and yield. Yield of ammonia, and decrease the rate of the reverse reaction. Region, oh dear. A flow diagram of the Haber process is shown. One way to reduce costs in the process is to use a heat exchanger to transfer excess heat from one part of the process to use in another part of the process. From the flow diagram, state another way that the manufacturing process maximizes profit or minimizes the impact on the environment. So, let's have a look through here and see if there's anything interesting we can use. So, we can't use this heat exchanger here, unfortunately, but a few things to say. I think it looks like we're recycling gases in there. We're also using air, which is a plentiful resource. So yeah, let's go and let's talk about the recycling of gases. It's probably easiest. I would just say gases are recycled. Not reactive gases, maybe. But other ones you could say is catalytic chamber, so you'll be using a catalyst which reduces the amount of activation energy needed to require, so it reduces energy costs and overall, or you can talk about air. Let's just talk about underground gases because it's probably easiest. Anyway, enough jabber on. Ammonia, goodness gracious, is currently being investigated for use in fuel cells. The reactions taking place at the electrode are this. So write the overall redox equation for the reaction taking place in a cell. So cast your mind back to maths, and basically what we want to do is get these two numbers to be the same. We want these electrons to cancel each other out. because we don't want electrons in our redox equation. Oh no. So to keep things nice and whole numbers, because I don't want to go in bloody fractions, nah, garbage. So I'm going to go and times that by 2. That'll get us up to 12. And then, of course, 4 goes nicely to 12. So that means I can times it by 3. So that means if I write all this out, be 302 plus 682. And I would leave everything in and then we start cancelling stuff out. 12E and then 12 OH. I'm going to have to write a bit smaller, aren't I? Cool. Now we can start getting rid of stuff we don't want. So 2OH on both sides, cancelled. 12 electrons on both sides, cancelled. 12 hydrogen, 12 water. No, you can't get rid of all of them. So we can actually cancel that. We can turn this into just 6. And then that means that we have 3 oxygens plus 4 nitrous things will give us 2N and 6 hydrogen water. So yeah, a bit of an overcon, but basically it's similar to you want to cancel out as many things as possible to make it as simple as possible. There we go. And there's our answer. Identify the reducing agent in the reaction taking place in the fuel cell. So if we go through here, we want to find the thing that is causing the reaction to be reduced. So we want to find something that is being oxidized. Well, can't be oxygen here because that's getting reduced. But ammonia, that's losing hydrogen, right? So that means that it must be getting oxidized, which means it's a reducing agent. So we can say ammonia. Seven, tap water contains a number of dissolved chemicals. In some parts of the country, tap water contains a high level of dissolved metal salts. State the term to use to describe water. Oh, I love this one. It's heavy. Oh no, it's hard water. It's hard water. Yeah. That's the kind of water I want. Soapless detergents are used with this type of water to prevent insoluble scum forming. The structure of the typical soapless detergent is as shown. The circle region of this molecule is the ionic and dissolved molecule. State the term used to describe this part of the molecule. I would say hydrophilic head. Because ionic stuff likes dissolving water because it's a polar molecule, polar solvent. Calcium ions are commonly found in tap water. The concentration of calcium ions in tap water sample was determined by titrating a chemical with a chemical called EDTA. Okay, a 50 cubic centimeters water sample is collected and reacted with a standard dissolution of EDTA with a concentration of 0.0045 moles per litre. The average TITA volume was 9.3 cubic centimeters. Calculate the concentration, or moles per litre, of calcium ions in the tap water. Oh, sorry, just stretching. Righty. So, let's go and run through. So, let's go and calculate the number of moles of EDTA. EDTA. Oh, that's a mouthful. So, N equals CV. We know the concentration is 0.0045. And the volume is going to be 0.0093. So, yep, I'm expecting an absolutely tiny number. And that's a problem with these redox, like you get these stupid numbers. Like, look at that, mate. Spend more time writing zeros than I do actually doing the question. There we go. So this is how many moles of ETTA we've done. I've used an ETTA is this chemical here, which means it's a 1-to-1 ratio of calcium. So we can just go back and say the for the 50 cubic centimeter. So we just do the same formula again. This time we know that it's this horrific number. Oh my god. Yeah, let me just get rid of those equal signs. Now we don't know what C is, but we do know what the volume is, which is 0.05. So then we can divide this by 0.5, 0.05, I suppose. I'll get an answer. Which is 0.0000837 moles per litre. Oh, SQA, why do you do this to me? Another ion found in tap water is manganese. Manganese 2 ions are oxidized to purple permanganate ions. The concentration of permanganate ions can be determined by measuring how much light is absorbed by the solution. The higher the concentration of permanganate ions in the solution, the more light is absorbed. The absorbances of several standard solutions of permanganate were measured and the results plotted. Whoa! A water sample had the absorbance of 0.08. Estimate the concentration of permanganate ions in milligrams per litre in this sample. Okay, so whenever you're doing this, what you want to do is draw a line through your graph and ignore that rogue value. So let's go and try our best to be about there. You think would be a good one? Yeah, maybe a bit lower. I don't know why I'm taking too much time on this, but yeah, that seems good enough. But yeah, they'll go whatever you line, as long as your line is passably a line of best fit. So estimate, it says we've absorbed to 0.08, so we're going to look at our line, and I mean 0.08, that's pretty much, that's about halfway between those two. So it'd be 5.1 concentration milligrams per litre. Seven, chlorine is added to tap water to make it safe to drink. The chlorine can react with substances in the water to produce trichloromethane. Trichloromethane is more soluble in water than tetrachloromethane due to the polarities of the molecules. Explain the difference of polarities of tetrachloromethane and tetrachloromethane molecules. Okay, so basically the difference here is that both of these contain the same C to Cl highly polar bond, but the main difference is that tetrachloromethane is symmetric, so all those polarities cancel each other out, so it's overall non-polar. Or trichloromethane has that one hydrogen atom, which means that you still have a full dipole over the molecule, which means it's easier to be dissolved. So let's go, and so that's why it's more soluble in water. Trichloromethane is polar, while tetrachloromethane is non-polar. Because trichloromethane is a permanent dipole due to its asymmetric structure, while tetrachloromethane is non-polar, has no dipole, no permanent dipole, due to its symmetric structure. Boom, and that's a poorly spelt way to do it, but there you are. Trichloromethane is used on an industrial scale to produce plastics. The first step in this reaction is to react it with hydrogen fluoride, HF. Using bond enthalpies and mean bond enthalpies from the data booklet, calculate the enthalpy change in kilojoules per mole for the reaction of trichloromethane with hydrogen fluoride. Okay, fine, I gotta pull out my data booklet in ages. Right, so I'll get rid of our calculator for now. So, the way I like to do this is I'm going to make a table. I'm going to have bonds broken. Bonds broken require energy, so I'm going to put it as positive because the values kind of swap from what you think in real life. So a positive enthalpy means it requires energy, it takes in energy from its environment, but a negative enthalpy means that it gives energy out into its environment. So that means when bonds made and they release energy, it'd be negative. Just helps me really get into the zone, you know. And then, well, what we're going to write, so bonds broken, we can clearly see here that we're going to be breaking free carbon to chlorine bonds. And I'm going to go and look in our data booklet and we'll find our bond enthalpies. So a carbon to chlorine bond is 338. And then we have a 1 carbon to hydrogen bond. Mean bond enthalpy is 412. Then we move up here, we've got 2 H to F bonds, hydrogen to fluoride, I mean, which are 570. And then, well, what bonds are made? So we have 2 hydrogen to chloride bonds, which are 431. And then we have 2 carbon to fluoride bonds, which is 484. And then we have 1 carbon to carbon chloride bond, which is we've already established is 338. And then we have 1 carbon to hydrogen bond, which is 412. So after all that, we basically have to add all this together, make sure that all these here are positive and all these here are negative. So 3 times 338 plus 412 plus 2 times 570. That was in this number, and then I want to minus everything. So we have 2 times 431 plus 2 times 484 plus 338 plus 412. I should be saying minus, but they're all going to this bracket, which will then minus, so we'll end up with minus 14. There we go. Oh no! It's our worst nightmare, everyone. It's another open-ended question. Oh, horrific. Dog food contains many different chemicals, including fats, vegetable oils, fatty acids, flavor and aroma molecules, protein, water, antioxidants, and emulsifiers. It is important that dog food has long shelf life, retains its appearance and texture, as well as providing sufficient nutritional value. Using your knowledge of chemistry, explain the role of different compounds in dog food. Okay, so again, what I like to do with these, well, what you probably should be doing is, remember, as I probably should have mentioned this before, these questions leave until the end. Don't do them, Phil, because they're very inefficient in terms of getting marks. Leave them till the end, see if you can do them, and write as much as you can, and you'll see how much time you got left. But don't do them in chronological order; it just doesn't make any sense. But other tip is that you probably wanted to list down 3 things that you want to discuss about. I made an exception for the titration one we did earlier because I had no idea what I was doing, to be honest. It was a bit of a hard one. But that one is more of a just write a sequence, you know, and keep talking about nonsense. But this one is more of a choose 3 things to write about. So let's go and choose 3 things to write about then. So let's go and talk about, say, fats is probably a good one. We can talk about glycerol and condensation reactions and dynamic equilibrium, emulsifiers and whatnot. So we can talk about that. Fats and vegetable oils are kind of the same subject. I'm going to say, let's do flavor and aroma molecules because those are probably going to be stuff like terpenes. Oh, if I can actually spell, I don't know how to spell flavor. It's right there. And aroma. So we can talk about that, and then maybe we can go and say, let's go and talk about emulsifiers as well, and then we can say it's other stuff as. But we've just chosen stuff from that list, and let's go and talk about this. So fats, fats and vegetable oils are triglycerides, because they're, as they are made of free fatty acids joining to glycerol. Or maybe that, and it's actually propan 1,2,3 triol. In condensation reactions, they are important nutritionally, as fats are required for living, I guess, required for biological function, as they are a vital component of cell walls, of cell membranes, I should say, sorry. Membranes. The degree of unsaturation of the fatty acids used in the triglyceride determine whether it is a fat or oil, as the greater the degree of unsaturation is in the fatty acids, the less neatly they lie together when stacked, so they can't lie as close to each other, so less intermolecular bonds can be formed, so have lower melting points. If the triglyceride is a solid at room temperature, then it is a fat, but if it is liquid, then it is a oil. Over time, fats and vegetable oils can undergo hydrolysis in the presence of water, leading them to break down into glycerol and fatty acids, which would sour the taste and reduce nutritional benefit. Right, I think that's probably enough talking about fats and vegetable oils there, so let's go flavor and molecules. Main thing to talk about here is you want esters and terpenes are usually used as flavor aroma molecules, so we can talk about them. So flavor and aroma molecules, and you have to spell it. are either esters, usually either, sorry, very inclusive, esters or terpenes. Esters are made of an alcohol and a carboxylic acid. A lot of this is going to be the same as the stuff we said up front because, well, fats and vegetable oils are esters, so which are joined together by a condensation reaction. Yeah, so same so far, but they have strong aromas and tastes. But they can break down over time with water. Through hydrolysis. Yeah, we could, I'm just copy and pasting here. It's probably a bit unnecessary to repeat it, but I've already written enough down. Through hydrolysis, back into an alcohol and carboxylic acid, which sours the taste and smell. And then we'll go and talk about terpenes. Oops. Terpenes are molecules made out of isoprene molecules. And that's the chemical formula. Ooh, C5. No, it's systematic name. Sorry, is what I was actually trying to. Yeah, it's 2-methyl butan 1,3-diene. And have stronger smells and tastes. They can be oxidized into terpenoids, which change the taste and smell. So dog food is best kept in a airtight container. Emulsifiers are molecules that stabilize a emulsion, preventing the liquids from separating into layers. An emulsion is liquid, is a liquid dispersed through another in droplets, and they are immiscible, which means they cannot mix. Over time, the emulsion will collapse, and the liquids will separate into layers, which would change the texture of the food. So an emulsifier is used to prolonged shelf life. I could probably keep talking about this, so we're going to do just a bit more about the structure of emulsifiers, and then we'll move on from there and see if we can complete this in paper this time this century. So emulsifiers use the prolonged shelf life. Emulsifiers are mono or diglycerides. So have a polar head that dissolves in the polar liquid and a non-polar tail which dissolves in the non-polar liquid. The emulsifiers molecules form a barrier between the liquids, preventing them from mixing, preventing them from separating layers. Right, let's think there's far more text than you ever need, but there you are. So yeah, you can write about a bunch of different stuff for this one. Anything in really, that would make sense. But anyway, I'll move on. So we'll go over to 9. Haloalkanes are alkane molecules that contain at least one group 7 atom. The table shows information on the boiling point of some haloalkanes. Using the information in the table, describe 2 different trends in the boiling points. Okay, well, as you can see here, as you go down the halogens, the boiling point always seems to increase. So let's just go and write that. So going down the halogen group increases boiling points. And then what's the other trend we can say? Well, it looks like if we increase carbon chain length, then boiling points also increase. So increasing carbon chain length also increases boiling points. There we go. Name the strongest type of intermolecular forces broken when bromoethane, this marker here, boils. So I believe a C to bromine thing should be non-polar, but let's go and double check if I can find my bloody dig booklet anywhere. There we are. So we look at the electronegativities of bromine and carbon. You can see that bromine should be all the way here, free, and carbon should be up here too. So yeah, 1.0 difference, which means there will be PD-PD interactions. But there's no hydrogen bonding here because hydrogen is not connected to is not connected to nitrogen, oxygen, or fluorine. So that means it'll be just PD-PD. So we're just going to say permanent dipole to permanent dipole interactions. Haloalkanes can be classified as primary, secondary, or tertiary depending on the position of the group 7 atom. Statewide 2-bromobutane can be classed as a secondary haloalkane. That's because the bromine atom is connected to a carbon atom which is itself connected to 2 other carbon atoms. So, we'll move on to 2. Draw a structural formula for an isomer of 2-bromobutane that is a tertiary haloalkane. Okay, so remember tertiary we've just established that we need to connect it to a carbon with the halogen to a carbon that is itself connected to 3 other carbons. So I think the strategy is for this. Oh, excuse me. As I'm going to just move this molecule here, this carbon down here, so we'll have this kind of cross shape of carbons, and then that means we'll have the same molecular formula, all the same atoms, but it will have a different structural formula with a tertiary haloalkane. So let's go and draw my cross subject, my cross like center thing. So it's probably going to look something along the lines of this, and then it's bromo. So we'll go have to do a BR, and then we just all we need to do now is populate the bonds with hydrogen. Spectacular, and that should actually be all you need to do for that one. Alkanes, excuse me, alkanes can react with group 7 molecules in free radical reactions to form haloalkanes. State is what is required for initiate to take place. So how do we split the this bromine molecule up in the first place? This is just one of the things you just got to remember. It's going to be UV, which stands for ultraviolet light. So that's light with high enough energy to kind of break the bonds there to create free radicals. Complete the table to show a possible termination step. Now, when we say termination, basically what's going to happen is we have free radicals that are going to combine into a termination reaction. So it's sort of like a propagation reaction, except it doesn't produce another free radical. It's just going to go and combine back into a stable molecule. So the easy way to do it is you could actually just reverse the initiation. So you could just say 2Br Br radical, and then you convert it back into Br, and that's actually completely acceptable. I think they would want you to have Br plus Br, because then it implies they're back colliding and back together. But yeah, you could just do that. That's probably the easiest way to do things. Or you could do a more complicated approach where you take free radical reactions from these two, like these free radicals, and combine them out together. But yeah, basically what you're looking for is you want a reaction that combines 2 free radicals into a stable molecule. But I'm just going to do the easiest way. That's done and dusted. Haloalkanes can react to form alcohols as shown. Depending on the structure of the haloalkane used, the alcohol produced can be oxidized to form an aldehyde or ketone. Compound P was converted to compound R in 2 steps. Okay. Compound R does not react with Tollens reagent or Fettling solution. Draw a structural formula for compound P. So what compounds are, when it says it's not reacting with Tollens reagent or Fettling solution, that means compound R cannot oxidize, which means that R is a ketone. So the double bond oxygen will occur somewhere in the middle. It won't be on terminal carbons. So that means when we go backwards, because effectively what we're doing here is we're just going to be replacing our double bonded carbonyl group with our haloalkane bonded group. We need to make sure it's in the middle of our carbon chain. So let's go and write that down. So remember, it's still C4, so we're just going to have C4, so 4 carbon atoms. And then either on the second or third, you're going to be able to put your Br, bromine, and then all you need to do from here is populate your hydrogens. And since we do actually have a molecular formula for this, you can just we can actually double check that we've got all our ingredients in the correct location. Well, we've got the correct numbers of ingredients, I should say. So of course we've got 4 carbons, and we have a single bromine, so that's fine. And how many hydrogens you have? We've 1, 2, 3, 4, 5, 6, 7, 8, 9, which is what we got. So we know that's probably the correct answer. The structure of 2 haloalkanes is shown. We've got 1,2-dichlorobutane and 1,2-dibromo-1-chloropbutane. Oh, they really get long names. The names of haloalkanes are derived from the structures using the following rules. The name is based on the longest chain of carbon atoms, and the presence of group 7 atoms is shown by shortening the name of group 7 atom. That's fairly standard stuff. The chain is numbered to assign numbers to group 7 atoms, and numbers should be assigned to the lowest possible numbers they are. So we would, for 1,2-dichlorobutane, we wouldn't start counting from here, because then we'll have 3 and 4. We want 1 and 2, so we want to start counting from the way that makes more sense. If 2 or more of the same group 7 atoms are present, use the prefixes di, chair, or tetra. The shortened name of group 7 atoms attached to the chain are listed alphabetically, ignoring the prefixes di, tri, or tetra for alphabetical purposes. Oh, they really do mess around. So, using these rules to name a molecule. So, first thing I always start when it wants me to name a molecule is I'm going to count the number of carbon atoms, because that's also what it says. And there's no weird branch change, so we're just going to have to go straight. Okay, well, it's going to be penta, pentan. And I don't see any OH groups or stuff along that line, so it's just going to be pentane. Now, what we need to do now is figure out what we've got. So we've got fluorine, so we go and have trifluoro, because that's what it says up here. And then we're going to have, I'll put the numbers in later, don't you worry. And then I'm also going to have, there's only one bromine, so I'm just going to have bromo. And then I've also got what looks to be a single chlorine. So I'm going to go and say chloro. Okay, but now we've actually got to go and arrange these in the alphabetical order. So obviously B becomes before C, which becomes before F. So I'm actually going to, all I need to do in here is actually just sort this around. And now I need to put some numbers on this. So looks like starting from the left and numbering 1, 2, 3, 4, 5 will probably give us the best solution. So bromine will be on the second atom, so it'll be 2 bromo. Chlorine is on the third, so it'll be 3 chloro. And then we have trifluoro, and all of them are 1, so it'll be 1, 1, 1, trifluoro, trifluoropentane. And there we go. A student was given a sample known to be a mixture of magnesium oxide and magnesium carbonate, and was asked to determine the mass of magnesium carbonate in the mixture. The first step was to accurately measure a mass of 1.3 grams of the mixture into a crucible using a balance. Oh no, I already see what's going on. Describe fully how the student can carry out this step. Okay, so what you're going to do is, firstly, you're going to zero the balance with the crucible. And then transfer 1.5 grams of the mixture into the crucible. And yeah, that's actually that easy. I don't know why I don't like these questions for irrational reasons, but they are actually fairly simple. But what you could also do is talk about weighing boats, but that's just adding an extra step. So like, oh, you measure the weighing boat and then you transfer it to the crucible. But but there's like, I'll put it here on the marketing scheme actually, but they've just got all these different bloody ways to do it. But you know how to weigh things, right? So looks like they're pretty nice with here. But they also they use the word tare instead of 0. So maybe that would probably be a better word to use, just to be absolutely sure of the markers. But there, that will do. The metal carbonates decompose on heating to give metal oxides and carbon dioxide gas. The apparatus was used to strongly heat the mixture of MgCO3 and MgO. The student used a pair of tongs to lift the lid from time to time. Suggests why the student has to lift from time to time. Well, it does say that it produces carbon dioxide. So, you know, you don't want carbon dioxide getting built from that, so you can say to allow the built-up carbon dioxide. Oh, I'm so dumb. Right, that's what you built up carbon dioxide to escape the crucible. Because, you know, gas volume expands as you increase temperature. So eventually this could actually force the crucible lid off, which you wouldn't want. So you want to make sure the carbon dioxide goes away intentionally. Explain why Bunsen burner is a suitable method of heating this reaction. Well, that's because you see here that none of these are flammable because they're both oxidized already. So it's like trying to burn ash, like you're not going to get anywhere. So you can just say reactants are not flammable. because you'd use a water bath to heat stuff up if stuff was available. So like, if you want to heat up wood, something for some reason, you might want to use a water bath instead, because otherwise it could catch fire if you use a Bunsen burner. Once a crucible has cooled, the final mass of the sample is determined. The mass of CO2 lost is used to calculate the mass of MgCO3 in the mixture in order to solve the film. Calculate the mass in grams of magnesium carbonate present in the mixture. Okay. So, we know we've lost this amount of grams, and the only way for that mass to go away, because the product would be a solid, right? So that means that this would all stay here, but carbon dioxide would actually decrease the mass. So first things first is I'm going to go and find out the actual difference. I'm going to turn my DPI down. That's not a 9. That is sort of a 9. So what does this mean? Well, I'm going to put my family down to the calculator. See what we get. We get 0.3404. Beautiful. So now that we have this, we can use it. This is basically the mass of the carbon dioxide, so we can use it to calculate how many moles. And it says we've got 44 grams there. So we divide by 44, and they give us this horrific number. It's 9. I'm just going to put ... We'll keep it in our calculator. So then all we need to do now is, now that we've got the number of moles of carbon dioxide, we can figure out the number of, we know the number of moles of MgCO3 because it's a 1-to-1 ratio, which means we can then just use the same equation. It's 0.0069 ... we don't know the mass, but we do know the formula mass, which is 84.3. So that means regular mass be 84.3 times that, and give us 0.582. And there you go, that's the answer, because it just wants us the mass. And then, oh, we're on the last page, folks. Another experiment to determine the mass of magnesium carbonate in the mixture involves measuring the volume of CO2 produced. The experiment is carried out by reacting the mixture of magnesium oxide and magnesium carbonate with excess acid. The volume of carbon dioxide gas can then be measured by collecting the gas with water as shown. So we actually going to need to make the production glass, and the way I'd usually do this is use a conical flask, and I might need to make this a bit bigger. Yeah, we'll make a conically oversized conical flask. But we want to mix magnesium oxide and magnesium carbonate with excess acid. So let's just go and put some acid in here, and then we'll have the mixture. And because it's in powder, what did I say powder? I can't remember. It just says okay. Well, I'll say it's powder because that's what I say. So we'll just say a powder. So maybe add a couple dots here, make it recognizable. I will label this so it won't be too bad, and then we need to put a big stopper in the top here. So I'm going to add a tube though. That will connect to here. Make sure your tube is not stopped. You don't want any lines in there. Right, and then what I'm going to do is label this. So let's go and add a label here. So this will be MgO and MgCO3, which I can make this text smaller, but here we are. That's readable-ish, and then we can just say that this stuff here is acid. So let's go hydrochloric acid, why not? And then other thing that's good to do is actually going to say carbon dioxide gas should be coming out. So label what gas should be being produced. So I'm going to say CO2 gas. And I'll go up around here and then we can pump it through. And on to the very, very last question now. So we'll suggest why carbon dioxide can be collected over water. And the reason is, well, if you're going to be doing that, that means it can't dissolve into water. So you can say that carbon dioxide is insoluble in water. There we go, folks. That was 2023 high chemistry paper. Yeah, exam will be soon, and hopefully I'll actually upload this video on the day that I make it. Oh, crazy. Never done that before. So yeah, good luck in your exam, and yeah, goodbye. Mash out.